Okay, another old exam question to look through. This one is about orthogonal diagonalizability, that mouthful, right? And so we saw that in section 9.3 that real symmetric matrices are orthogonally diagonalizable. And a pretty reasonable question to be wondering is why should I care? What does that matter? What does that have to do with anything? Well, this old test question actually gives a really good application of that fact, that specific fact. Okay, so let's dive into it. Here it is. We are looking at 1617 fall, exam 3, and we are going to go over to question 4. And first, we'll just go through the problem as written. It's actually only the first 2 parts that we need for this observation. So we start off with a callback to this thing called the Hessian matrix. And you may recall this from Math 212, from multivariable. We were doing optimization. This matrix, we were never given any justification of why this was, but this matrix is part of the second derivative test, right? So specifically, if this matrix here, if its determinant is positive, then you either have a local max or a local min, depending on whether this one element here is negative or positive, respectively. And if this determinant's matrix, this matrices determinant is negative, then we declare it a saddle point and no further analysis necessary. And we did not see any reason why that would be the case. And that's what we're going to be able to do now with this question. So anyway, first let's get the work done, and then we'll be able to make the interpretation. So how do we know that this Hessian matrix must be orthogonally diagonalizable? Well, now strategically, if we want to show, right, if we want to show that something is orthogonally diagonalizable, we really only have one such theorem, and that is the case for real symmetric matrices. And well, we are reminded right here that these 2 numbers are equal to each other, and therefore we're looking at a symmetric matrix. And so we're looking at real valued functions, so these are also real. Okay, so real symmetric matrix, therefore orthogonally diagonalizable. Okay. All right. Now, the next part of the question, things do get a little bit hairy here, but it's just a matter of slowly and carefully, and taking a deep breath, and keep your cool. But it claims right off the bat that the second order behavior of a function is described by this expression right here, specifically 1/2 of that expression. So where did that come from? Little digression. We'll talk about the context. Why? Where is really that describes the second order behavior of a function? Yeah, turns out it does. And so I want to point out this formula up here. This is not in the book. I don't think it's in the Math 212 textbook either. This is the second order Taylor polynomial for a function of 2 variables. And it's not such a big surprise. I mean, you'll notice it actually looks a lot like, here's the first order Taylor polynomial. That's pretty believable, right? Value plus derivative times delta x, right? It looks just like the formula for the first order, the single variable first order Taylor polynomial. So not a big stretch there. And I claim that this is what the second order term looks like. Now, how do I persuade you that this is what it looks like? There's an easy exercise that you can do with a little bit of tedium to write down. Not so bad though. You can directly confirm for yourselves that this function has all of the same values and derivatives as this function, the function f, that's being referred to here. These various partials make up the Hessian. T and f have the same value at the point A. T and F have the same partial derivatives at the point A, and T and F have the same second partials at the point A. A direct calculation. You plug in x equals A. Obviously, if you plug in x equals A, then that becomes 0, that becomes 0. And so all of this disappears in a puff of smoke. And there you go. We plug in x equals A, and T of A is F of A. Analogous calculations for the partial derivatives and the second partial derivatives. And you'll find that they all check out. Okay. So this is the second order Taylor polynomial because it mimics F so well in terms of, well, of course, values and partial derivatives. Okay, so I claim that the second order behavior is described by this. Well, yeah, specifically half of that. I left the half off in the statement of the question. Not necessary, right? This is the second order behavior because it's the second order term in the second order Taylor polynomial. So that's where this comes from in the first place. Okay, so what we're supposed to do now, it asks us to rewrite this as that expression right there for, some vector. We don't need to worry about what z is, but we need to show that we can rewrite that expression in this form. And then there's a big hint here. Don't forget that orthogonal matrices preserve dot products. So that's going to come up at some point. All right. Well, again, slowly and carefully. This expression, don't forget H, right, is diagonalizable. Right, that's what it means to be diagonalizable. It's conjugate to a diagonal matrix, D. Okay, now wait a second. It's not just diagonalizable. This matrix is more than that. It is orthogonally diagonalizable, right? So orthogonally diagonalizable means that not only is it conjugate to a diagonal matrix, it is conjugate by way of an orthogonal matrix, or said differently, an orthogonal change of basis, right? So wonderfully, this P matrix, not just a random matrix, P is orthogonal, and because it's orthogonal, several nice things happen, but what we need in particular about P and therefore P inverse being orthogonal is that they preserve dot products. Okay, so because dot products are preserved, I can multiply in this, clean up my mess. In this dot product right here, I can multiply both sides of the equation, or both sides of the dot, by P inverse. P inverse preserves dot products, and that means that this dot product is the same as the original dot product. Okay, so said differently, this P inverse right here, right, because P inverse preserves dot products, doesn't do anything. So let me say it like that. This dot product is equal to this dot product. Okay. So now a little bit of convenient algebra that cancels with that, of course, and therefore we get this expression. And believe it or not, we're actually kind of done here, because what we've got is a thing that I'm just going to call Z, right? And we've got this D matrix right there. And whatever that Z is, well, it doesn't really matter what it is. I can crank out this expression, right? Z dot DZ. Well, DZ is easy to write down. D is a diagonal matrix, real easy to multiply that out. And so therefore Z dot DZ is this, which is that, which is what we wanted. Okay, now that's, like I said, it's a little hairy, a little weird, but notice all I've done in this question really is go through and use what we know about the matrix. So specifically, I knew that H was diagonalizable, so I can write this. I capitalize on the fact that this matrix and therefore this matrix also preserve dot products. And there it is. It kind of falls into our lap. Now, with tricky bits, but nevertheless, it's just using what we know. Okay. All right. Now, there's a part C. We don't need to look at part C for what we want to do with this recording. What I want to do is show you how valuable it is to know this, to know that this can be rewritten as that. And keeping in mind that that is, in fact, just this. Namely, that is the second order behavior, right? So the second order behavior of my function is described by that expression with lambdas and z-squareds. And that has a very nice form, very simple form. You can see the squares right in there. That's the squares are always positive. We're going to be able to draw some nice conclusions about this second order behavior by simply knowing that it's equal to that. So notice I've got that noted up here. Oh, let me come up here. Right, this second order behavior can be rewritten like that. And that's our foot in the door. And here comes the rest of the calculation. Let's, oh, where's my, here we go. I'll try to fit this all in on the page at the same time. So yeah, let's try to remember the second derivative test. Right? Think back to Math 212, second derivative test. And again, you write down this thing called the Hessian matrix, right? And you take its determinant. And if its determinant's positive, then you got to look at the fxx. You got to look at that top left element, and that decides if it's a max or a min. And if the determinant's negative, you declare a saddle point and walk away. Let's try to see now, with the benefit of knowing this, how do we know that works? And here's how it works. Ultimately, not such a big deal. Don't forget the determinant of H. Well, H being diagonalizable, the determinant of H is the determinant of that product. Multiplicativity lets me multiply that up into three things, two of which cancel. And in fact, I get it's just the determinant of D. D, of course, being a diagonal matrix whose determinant is really easy to write down. So this determinant that we computed, it's the product of these two eigenvalues. That's these two eigenvalues here. So knowing this determinant, knowing if that determinant is positive or negative, that's really what that is a foot in the door for understanding whether those terms are positive or negative. Right, and that's most of the idea right there. And there, everything else that's about to follow is mostly just kind of little details. So let's carry it through. Suppose the determinant's positive, right? That's this thing right here is positive. Well, there's really only two ways that can happen. Either they're both positive or they're both negative, right? And in those cases, we get to draw simple conclusions. If these numbers here are both positive, then I've got a bunch of positive stuff here, right? If both of these eigenvalues are positive, well, and of course, certainly these squares are always positive. I've got positive plus positive, that's definitely positive. And if the second order, keep in mind here, what we're looking at is this expression is the second order behavior of my function. If the second order behavior is always positive, then I've got a local min, right? If the second order, all the second order terms are positive in every direction, no matter what you do, it's always going up, then you've got a local min. Okay. Now, likewise, if the determinant being positive comes about by the eigenvalues both being negative, let's just say hypothetically, what if they're both negative? Well, then again, it works out very nicely. That's negative and that's negative, and therefore this whole expression is always negative. And if your entire second order behavior is always negative, then that means you've got something kind of like this. Every second order term, always negative. That means you've got a local max. Okay. All right. Now, that's not the way, of course, that the theorem is stated in the second derivative test. In the second derivative test, when the determinant is positive, we direct the user to look at the top left element of the matrix and see if that's positive or negative to distinguish these two cases. So why would we look at these at the top left element? This is just a clever little observation, but that top left element happens to be, coincidentally, one of the values of that second order behavior. If it's positive, right? Hypothetically, if this is positive, well, then we know that that expression is not always negative. If it's not always negative, well, then it's always positive. Again, we only have these two cases. So this is just kind of a convenient little hack, really, for distinguishing these two cases up here. Okay, now we're only most of the way done, right? Remember the old second derivative test. If the determinant's positive, then you look at that to distinguish between these two possible cases. But there's also the possibility of what if that determinant is negative. So, well, what if it's negative? What happens if it's negative? Well, if it's negative, and don't forget what it is. Don't forget this determinant is that product. If it's negative, these two numbers have opposite signs. Right? Again, that's how pluses and minuses work, right? So if that determinant is negative, those have opposite signs. And if you think about it, then if exactly one of these is positive and exactly one of these is negative, I don't know which, right? Kind of doesn't really matter which. If one's positive and one's negative, then this expression will be sometimes positive and sometimes negative. And there's just kind of no way getting around that, right? So therefore, this expression is, well, it's sometimes positive and sometimes negative. And therefore, the second order behavior of the function is, well, it's sometimes negative and it's sometimes positive. And this is the tough, right? It's kind of curved. It's going to be curving down in some directions, but it's also going to be kind of curving up in some other directions. And again, that's what we call a saddle point, right? It's neither a max nor a min. So that's a saddle point. So anyway, that's where that all comes from. And I think it's wonderful how this is all a consequence of a little bit of linear algebra. Those of you who took my Math 212 heard, well, you heard at least this part about the second derivative test, about the specifically about the second order Taylor polynomial. But how we use linear algebra to break this down, right, is what we've learned here. That the orthogonal diagonalizability is the needed trick. Diagonalizability is what allows you to get to this. The orthogonal diagonalizability is what allows you to get to this, aka this. So it is explicitly, it's because we're looking at a real symmetric matrix. It's because these derivatives are equal to each other that I have a real symmetric matrix that allows me to get these two tools that I need in order to be able to make this algebra all work out. So anyway, that's where the second derivative test comes from for 2x2 real valued functions. So I think that's a nice application, and also kind of closes a loop, fills in a blank from Math 212. Okay, so I hope this has been useful.